right, so we're going to interpret some graphs. So one of the things we're going to find is all of those patterns that we did, that we could create an equation from, we can put those onto a graph. And then you can figure out things that are not even in your table of values. So here's the first example that we're looking at. And what we're going to notice is when a table of values is made, that we always list our x values first and our y values second. So if our x values are listed first, under this graph, we can write speed is going to be along the x. And we'll write the units. Speed is in kilometers per hour. And on our y-axis, it's stopping distance. Does it make sense that the faster you're going, the longer it takes to stop?
Yes.
And our coordinate practice at the beginning was so that we could think of each of these as coordinates. We have 15, 5. So if I go on my graph and I label, I go 15 in the x and up 5, just like we did in Battleship, that would be the point 15, 5. And then we have 30, 17. So I go 30 in the x first and then up 17. Estimate to the best of my ability where that would be, and I could label that point 30, 17. I'd like you to draw the other 3 points on the graph as well. Okay, some things to notice. Do you notice that your dots make a straight line? Okay. That if you joined your dots together, they would make a straight line. So we would say, is this graph linear? The answer would be yes. Sometimes, to check if something is linear, you can look for patterns in your table of values. What am I going up by each time here? $12. Excellent. So we notice a pattern that we're going up by the same amount on this side. But this is the first one we've ever had this happen. Because in all of our figures that we've done, what have we always done? Like 1, 2, 3, 4, 5, right? But now this side's going up by 15. That's a big difference than going up by ones. The formula for this one is a little bit trickier than other ones. The formula for this one is going to have, I'll write it in this color, see if you can figure out where these numbers come from. You know how our formula in the other ones always had this number times x? Look at now. It has this number 12. That 12 still gets multiplied by the x, but you'd also have to think about that 15. So it gets 12 divided by 15. And then if you plugged in a number, right? If I plugged in 15, 12 times 15 divided by 15 would be? This is easy without a calculator. What's 15 divided by 15? Okay, so 12 times 15 divided by 15 would be 12 times 1 would just be 12. What do we want to get? We want to get 5. So we would have to subtract 7. That's our formula for this one. A little bit more complicated because it has that fraction in there. But all that work we did with fractions in the first semester was, again, to help us get ready for something like this. So there's our formula for this graph. And one of the things that we're going to find out is that formula is actually the equation of this straight line. Okay. We're getting a little bit more, that's like the next stage of complication. Right now we're just looking at the pattern. Are we able to draw the graph? Perfect. Once you have a graph, there are two things that you can do with a graph to figure out new values. There's something called interpolation. This is on your next page. You might want to highlight these definitions if you have a highlighter. I love highlighting, so I'm going to go yellow for this one, green for that one. Interpolation is estimating a value within your values, and extrapolation is estimating a value beyond your values. So in my example here, with speed and stopping distance, do you see that we had speeds between 15 and 75? So if someone said, well, what happens if you were going 50 kilometers an hour? When or how long would it take you to stop? That would be interpolation, because the 50 is between our values. And if I wanted to interpolate 50, I could go to 50, go up until I hit my line, and go across and say, what does that look like? At 50, I would estimate 32. Perfect. I would estimate 32 meters. Makes sense, because that 50 is between 45 and 60. Okay. That choosing 50 is interpolation, because it's between the values that we would have. Okay? But if someone said, what happens if you went 90? Well, 90 is past 75. You could still go up until you hit the line. What does it look like? At 90, what would our estimate be? 65? That would be outside of our values. That's called extrapolation. So interpolation is when you're looking at stuff within the data you have. And if you'd like to extrapolate, then you're looking outside of your data. So these are two important definitions for estimating. They've got one for estimating within your values and estimating outside of your values. So what you could get is you could get a question that has a graph. Here's a graph, air temperature recordings at different altitudes. So as you go higher up from sea level, that's your altitude, the temperature seems to be going down. It would be really weird if it was the opposite. Then the hottest place in the world would be Mount Everest, because you'd be like, oh, that's the highest. And anytime you go to the ocean, it'd be really cold. But I don't think it works that way. It's the opposite. The higher you are above the ocean, as you go up in mountains, the temperature gets colder. And so sea level is sort of the lowest, so it's always warmer at the ocean. Okay? Yes. Let's go through these examples first. So what is the temperature at 1,000 meters? So we would go to our graph. We would find 1,000. And this is the work that you would show. You draw a dotted line up to the line, and then you draw a dotted line across. And you use that dotted line. You know, if you have a ruler, it's even better, because it can be perfectly straight. What do you think the temperature is there? Looks like 2 degrees Celsius as an estimate. If we looked at 600 meters, again, we would go up from 600 till we hit our line, then across from there. Is that perfectly in the middle, would you say? 7.5 degrees, or do you think it's higher? And again, it's an estimate. So the nice thing about an estimate is if you wrote 8 degrees, I would say that's a good estimate. If you wrote 7.5, you wrote 7, those are reasonable. If you wrote 13 degrees, you'd be like, no, that's not even close. You know that it has to be somewhere between 5 and 10. It looks like it's right in the middle. You should be able to get a good estimate what's right in the middle between 5 and 10. Both of those were interpolations because the data that we were given sort of looks like it started at 375 or 350 and went up to 1800. So these ones, maybe we want to write a note here. To practice our definition, that these ones are interpolation. We were looking within our data points. We can also interpolate and extrapolate if they give us the other thing. Now they want to find the altitude at 5 degrees and 10 degrees. So I'm going to keep switching colors here. If I go from 5 degrees over, I hit the line right there and then go down. That one looks like it worked out perfectly to be at 800 meters. And the next one at 10 degrees, another color. "10 degrees looks like 450 meters. What do you think for these ones? Were both of those extrapolation, both interpolation, or one interpolation, one extrapolation? Was it within our data that we found that? Or did we have to go beyond our data? Beyond. Okay. So I guess one way that you can sort of see this and figure it out, I'm gonna take, this is where my data started at this red point, and this is where my data ended. So anything that hits the black line is in those 2 points. So again, both of these ones are going to be interpolation. If I extend the line beyond what was given, so if I drew this farther this way or farther this way, anything that would hit that red line, that would be extrapolation. So you have to sort of look at your endpoints. If we look back to our first example, where was our first point? At 5, 15, 15, 5. Where was our last point? At 75, 53. So anything beyond in this way and beyond this way, that would be extrapolation. Anything that hits the green line in the middle, that's within our values. And so a big thing about this definition to help you remember is the fact that interpolation starts with the word in, right? And extrapolation, you can actually look at the word extra. It's beyond what you had. It's extra to help you remember those definitions. Oh yeah, Duncan's not here. I don't even...
What is that, Logan?
All right. Describe what is going on in this graph. So we look at the graph, we look at time, and as the time is increasing, the distance is increasing. So you're driving maybe away from home or something like that, and the longer you drive, the farther you travel. That seems to make sense. Describe what's going on in the graph. The longer or the more time you take, the farther the distance you travel. So the more time you take, the longer the distance you travel. Now what we're going to also do for this one is we're going to make a chart with the points that we know. We always put the x-axis first. The x-axis was time. The variable was t. The y-axis is distance, and the variable they're using is d. D for distance, T for time. I wonder where they came up with those letters. Unbelievable. There's 4 points on here. 1, 2, 3, 4. What's the first point? 2, 5. So the time is 2, the distance is 5. The second point? 4:11. And then 6? Where does the 6 look like it's at? 17? Does that look like it's 17? Where does the 8 look like it's at? 23. Do you notice a pattern here? It's going up by 6 every time. Is there a pattern on the time? 2. It's going up by 2. The formula for this one. The formula for this one would be y, or not y, because our y is distance. Distance equals, and check out these numbers, 6 and 2 times time. Now we have to figure out what makes it work. What is 6 divided by 2? 3. Okay, 3t. Now, if I plug in 2, 3 times 2 is 6. We need it to be 5. Minus 1. Check out if this formula works for 6. What's 3 times 6?
3 times 6, that's 18.
18. Minus 1?
17.
It works. This is the new pattern we're starting to see. Okay? Can you see how I've color-coded it to see where you would get those numbers from? Did you notice in all of our other ones, we just went by the green numbers in our patterns? Because we were going up by 1s. We could have had, if you were going up by 3 and the other ones were going up by 1, you could do 3 divided by 1, which would be 3. It would work as well. How much time has passed after someone travels 5 kilometers? So which 5 am I going to look at? This 5 or this 5? Okay, look at the question. They tell you 5 kilometers, so we need to go from the 5 kilometers over and down and write 2 hours. 15 kilometers. I'm going to switch colors to green. 15 kilometers is here. I go across, hit the point, go down. It doesn't quite look at 5.5, does it? Maybe I'll do 5.4. 5.4 hours. And then one more color. Oops. Yeah. Oh, I skipped some. Sorry, guys. I skipped to the bottom questions first. I skipped to the bottom questions first. 3 kilometers? Hey, do you notice that if I do 3 kilometers, which is right here, it doesn't hit the graph? So I'm going to go, these were my endpoints of my graph. I could extend it, and at 3 kilometers, I would hit the part that's extended. Looks like at 1.6 hours. 1.6 hours. These two are interpolation. This one is extrapolation. Oh, trying to get me back in. Thank you. And we skipped those other ones, so we'll do those right now. Let's look at 6 hours, 5 hours, and 9 hours. What is the distance traveled after? So we go on to our graph. I'm running out of colors. 6 hours, I'm going to go up from 6, hit the point, go over. This is a nice one because it's already on our graph. 17, the distance was in kilometers. 17 kilometers. What colors haven't I used? Let's go black. Good choice. Next one was how many hours? 5 hours. 5 hours is right here. Hit the line, go across. I think 13 kilometers, good estimate? 13 kilometers. And 9 hours, bright yellow. 9 hours hits the red line. It's like at about maybe 27. Boy, writing in yellow, I think you guys would be like, is that hard to see a little bit? Wow, it's hard to see on my computer. So again, these ones were interpolation because they were in our data. This one hit the red line. That's outside our data. Extrapolation. So you can see that sometimes if you color code things, it can be really helpful for understanding or seeing what's happening. So now thinking about this same thing, the question is, are there values that would not make sense to extrapolate on here? So we've got the time you've traveled and the distance you've gone. Sometimes when you go beyond your data, it's extrapolation with the red line. Are there extrapolation times that actually don't make any sense with this question? 0? Okay. I like, based on our graph, at 0, apparently you would travel backwards. So that seems to not make sense. What about negative hours? Does it make sense to travel for negative 3 hours? Like, maybe if you had a time machine, you could go back in time, but I don't think those exist yet. Why? Oh. You would be like, oh, that was such a good math class. I want to go back in time and do it all over again. So, can you interpolate values for this graph? So again, anything within your data, I'm going to draw with a black line. So it started here. I'm going to connect those dots to there. Anything that keeps going would be extra. That's if we join those lines. Okay? That's the idea. Interpolation would be picking a data value that's not included. So they gave us these 4 data values. Can you interpolate something that's not included? Well, 1.5, right? But then the next thing you have to consider is if you went to the grocery store, could you buy 1.5 cartons of ice cream? Right? You just walk into the grocery store, you bring a big knife along, right? You go in, you take out the ice cream out of the freezer, you take out your big knife, you cut it in half, put part back, and then go to the store and say, I'd like to buy 1.5 things of ice cream. What's going to happen? Probably security is going to be like, there's a guy in here with a knife, he's attacking the ice cream cartons, help. So you can't buy half of an ice cream carton. So interpolation doesn't make sense. And in fact, even joining these dots that I did at the beginning actually doesn't make sense in this situation because you can't buy a half of an ice cream carton. Yeah.
You have to be smaller.
You're like, be like going and buying Skittles and say, I only really want one, so I'm going to just open this package. You count out that there's 40 in the package. It was normally $2 for the package, but divide by 40, that's 5 cents. So you just take out the green one that you want, give them a nickel, and then walk out. Now you're curious how many Skittles are there in a bag. That is a good question. We need to know this question. But it would make sense to extrapolate because you could figure out how much 5 would cost. Right? According to this, if we look at our table of values for this one, we've got number of cartons here, which is n, and the cost here, which is big C. You buy 1 carton, how much does it cost? $4. Look at the chart. 2 cartons. Oh, no, we're just using two would cost $8. 3 would cost $12, and 4 costs $16. What's our pattern here? You're adding 4. What's our pattern here? So your formula is going to be, and again, I'm going to use these numbers, 4 over 1. Notice that 1 you don't really need, but it's there. Times by, oh, this is not y. This time the second letter is C for cost, and then n for number. Let's check it out. If you plug in 2, what's 4 times 2? 8. What do you have to add to make it work? 0. You don't have to add anything. So our formula, does this make sense? It's $4 times however many you buy?
Yeah.
Perfect. So we can practice getting those formulas as well.